It's electric, and in a Cirrus, that means dual alternators, dual batteries, and a smart redundancy that makes your life a whole lot easier. So why is it important to understand how this system works? Well, when something goes wrong, a pilot needs to be able to understand how to identify the issue as well as troubleshoot and remedy the situation in the event of an emergency. Hi, my name is Carly, and today I'll be going over the SR20's electrical system. The Cirrus SR20 runs on a 28-volt direct current as a way to reduce the risk of system faults. This system is what powers the avionics, the flaps, the lighting, and other electrical components while the engine is running. As I mentioned before, there are two alternators inside this aircraft. Both of them are belt-driven, while alternator 1 has a limit of 27.8 volts and 100 amps. Alt 2 is 28.7 volts and 70 amps. Now, what is an alternator and what are amps and volts? Well, the alternator you can see as the power plant of the electrical system. You can think of the alternator as the main source of power that is charging everything else in the aircraft. Now, amps and volts, you can use a water tank and hose analogy to kind of make it easier to understand. The volts are the amount of water that you have, your capability of carrying, whereas your amps are the constant speed or the flow of the water coming out. Moving on to the two batteries inside the aircraft, we have battery 1, which is a 24-volt 11-amp battery, and battery 2, which is two 12-volt 7-amp batteries. Now, the most important thing to note is that the batteries are charged through the alternators, which is why they have a higher voltage than the batteries themselves to be able to charge them. It's also important to note that the batteries is what starts the engine as they are powering the starter directly, and the alternator is not supplying any power until the engine is running. The name belt-driven or engine-driven alternator. Now, before we dive into the power distribution charts, I just want to give a disclaimer to read your own POH prior to taking any information from this video. Diving right into the power distribution, we have our master control unit, also known as our MCU. And inside this control unit, we have our main distribution bus 1, main distribution bus 2, and our essential distribution bus. This is just categorized as how this power is being distributed across the system. So what is a bus? Well, a bus is like a school bus in a sense, whereas your passengers are electrical currents traveling from places like the school, being your main distribution bus 1, to a transfer station, which is our main bus 3, and then your home location, which could be your landing light. That's where that power is being supplied, and it's following that route along. So just for a quick recap over everything that we've talked about, we have our master control unit, our main distribution buses, our essential distribution buses, and our two alternators and our two batteries. As long as we understand before going into all of the routing and the plates that the two alternators are not only just charging the batteries, but they're also supplying power to that master control unit. The power is supplied, and we're about to dive into how. We're not just going to look at the routing, but also how to read these schematics or these plates, as I've been referring to them as. So looking at the symbology on the schematic itself, battery 1, anytime there's a battery on these types of charts, it's going to have those dashed lines that are kind of uneven. A switch is going to have those two dots with the line sticking up. Whenever a switch is activated, it will drop down and connect that circuit. The relay has that little top hat above it. Whenever a relay is activated, the little top hat will drop down and connect that circuit again, kind of similar to a switch, except there's not a physical switch that's being flipped for a relay to work. Now, looking at what a fuse would look like, it's going to be that little S shape that's going to just restrict the amount of amps that are allowed to travel down that circuit. And a voltage regulator is going to just ensure a constant stream of energy flowing down those wires. So going on to our external power, this would be used in the event of a jump start, cold weather start, or a maintenance prolonged. It's an external plug for the plane to be able to get power into the system. So moving on to the little triangle with the line in front of it, that's called an isolated diode. It allows the travel of electricity from one direction to the other, but not in the opposite. So in other words, power would be able to travel from main distribution bus 1 to main distribution bus 2, but not in the opposite direction. So it would not be able to go from distribution bus 2 the main distribution bus 1. Going on to the circuit breakers next. Circuit breakers' purpose is in the event of an overcharge of electricity, they will pop rather than overcharging the component that it's supposed to be going to. That's a safety feature for us. We can pop the circuit breakers back in. The general rule is if one pops out, push it back in and test it. If it pops out a second time, it's now in op. Do not touch it again. The next thing we're going to look at is that funky looking triangle with a parallelogram on top. That's called the transient voltage suppressor. That is in the event of a lightning strike that will dissipate the energy across the circuit board, preventing it from blowing out one side or another. It's kind of like a beam that is allowing multiple weights supported across it rather than absorbing all that energy itself. And that last bit that I had highlighted was the grounding symbol, which allows a fault path to have less resistance to prevent damage to the other electrical equipment, basically just letting any additional charge coming off rather than going back into the circuit. So moving on to the actual schematic itself and how this electricity travels, I've highlighted the master control unit that we talked about earlier with all of those main distribution buses and essential distribution buses inside. So one thing for us to take into consideration also is that charge works by the highest voltage available. So alternator 1 in this case would be charging directly that main distribution bus 1, even though it's a lower charge than alt 2, just because of the fact of that isolation diode that sits between main distribution bus 1 and main distribution bus 2. So now we can see that main distribution bus 1 has 5 routes total, 3 without isolation diodes and 1 to the essential bus and the other 1 to the other main distribution bus 2. Following the routes, the way that the electricity would travel is that it would come out and over and down all the way to main bus 3, like those transfer stations that we were talking about earlier, right, with the school bus analogy. So here's main bus 3 and it's applying power to the main bus 3 with the landing lights, EVS camera, 12-volt USB power, and MFD alpha. Looking at this chart, this is how the electricity would normally travel. The main distribution bus 2 is not normally getting power from alternator 1, it's usually getting power from alternator 2. It's going to prefer the higher voltage available, and alt 2 has a higher voltage than alt 1. However, in the event that it were to fail, that electricity would then travel along that route that does have the isolation diode, but it allows travel in that direction from main distribution bus 1 to main distribution bus 2. This is another redundancy to ensure that our electrical capabilities don't collapse. So going into the battery 1, this is what's going to be powering the starter. So when that switch is flipped, that circuit is connected, the battery emits a charge, the relay will drop, connecting that circuit again, and the starter will have power. Now, in the event that alt 1 were to fail and alt 2 were to fail, that battery 1 is still capable of charging that essential distribution bus, which is again another redundant system to ensure that we don't have total collapse of our electrical system in the event of an emergency. So let's say that both our battery 1, alt 2, everything has failed except for that battery 2. Well, that switch will kick on, that relay will connect the circuit, and that battery 2 is going to start directly charging that essential bus 1. Now, the power does travel back up. It will power the whole bus, but it's also going to send it back through to the essential distribution bus, which would then power essential bus 2. Keeping in mind that there's always a direct current to essential bus 1, but essential bus 2 is charged or given electricity via essential distribution bus. Now all this information is in the textual description of the battery 1 and battery 2 switches, and it does describe how this travel of electricity goes, but to make it a little easier, I did draw it out so you can visually see how it would work. Now again, this is all happening instantaneously. It's as fast as electricity travels, which is incredibly fast. Let's go into how this information would be displayed or how you would use this as a pilot. So anytime that there is some kind of failure on input for any of the components in the aircraft, it's going to have a big red X on it. There is a crew alert system or a CAS system in the Cirrus. It's located to the right of the altimeter and vertical speed indicator, and the engine page on the Cirrus will also show the corresponding CAS message color as well. I just wanted to also put in a caution to always check your personal POH or school documents or any kinds of notes from the manufacturer when it comes to any kind of issue inside the aircraft. You always want to use whatever the POH recommends, as it is coming directly from the manufacturer. There are a lot of caution notes underneath the electrical page, and I highly recommend checking those as well. But I hope you've learned something new, and have a wonderful rest of your day. Carly out.